Hey Team Physics, welcome back to the first screencast of the spring term. So we are going to be studying sound and light this spring term, and in order to understand sound and light, you're going to need to know a little bit about what sound and light are composed of and how they are transmitted. So we're going to spend today's screencast talking about vibrations and waves. I'm going to write that down here. Vibrations and waves. Now, a vibration, you can think about a vibration as a wiggle in time. And I'm going to explain that right now. So imagine you have a bell. My drawing skills put to use. Wait. Okay, this is a pretty terrible bell. Let's make it the Liberty Bell. Put a big crack in it. Okay, imagine you have the Liberty Bell and you strike it. Well, when you strike it, it will start to vibrate back and forth. And it rings. It makes a sound. Vibrations need time to vibrate. They vibrate back and forth, but on net, they don't move through space. So you hit the bell, it rings, but when it finishes vibrating, it's still in the same spot. So on net, it doesn't move through space. So a vibration is a wiggle in time. And now this is in comparison to a wave, which travels through both space and time. So when a wave propagates, it moves from one location to another. Both light and sound are examples of waves. They move through both time and space. Okay, so let's backtrack a little bit and talk about something that we did in the fall term. Okay, imagine we have two balls, and one is twice, or it's bigger than the other, maybe a little bit more than twice the size of the other. And they're held the same distance, let's call it h, from the ground. If we drop these two balls at the same time, which one hits the ground first? I'm going to pause this for a second and let you consider that. Okay, end of consideration period. Well, you would be right if you said that both balls hit the ground at the same time. We know this from our study of motion in the fall term. In the absence of air resistance, all things accelerate with the same acceleration due to gravity, 9.8 meters per second. Okay, that was a little bit tricky. I'm going to give you another one. Okay, now we have the same two balls, and now they're on an inclined plane with the same height h. If we release them at the same time, which ball hits the ground first? Again, in the absence of friction, assume this is a frictionless surface in the absence of air resistance, these two balls hit the ground at the exact same time. Ooh, so this one, we lost a bit of the ball there. And this one, oh gosh, I'm bad at this. Both of these, okay, you get the point. Both of these hit the ground at the same time. Again, this is because the acceleration due to gravity on each object is the same regardless of their mass. It's going to be 9.8 meters per second. Okay, so third question. Imagine you have two pendulums, each with the same length rope, and you let them swing. Back and forth. Which one swings faster? Again, they're going to swing at the same time. The rate of swing of a pendulum is independent of the mass attached to the pendulum and is only dependent on the length of the string that the pendulum is attached to. If we were to extend this pendulum and give it a longer rope, then we'd see the time it takes to complete a cycle for this small mass pendulum would increase. You guys probably have experience with this. Something on a longer rope swings more slowly through space. Okay, now you might wonder why we are talking about all of this, and I'm going to tell you why. Tell you how it relates right now. So, I'm going to go to a new page with the same pendulum. Okay, now the arc of the pendulum is probably a little bit more like this, swinging back and forth. Now imagine we were to suspend this pendulum over a piece of paper, and we were to fill the ball with sand, yellow beach sand, to remind us of spring break. Okay, and we were to leave a little hole in the bottom of the pendulum so that sand dripped out as it swung back and forth over the paper. Well, we would see that it would trace a straight line over the paper like so. Every time it swung back and forth, it would trace another line over the same point, swinging back and forth just like this. Okay, now let's take this same scenario and paste this right next to here. And I'm going to delete the sand that we've dripped out here. Now imagine that while we're doing this, swinging the pendulum, we move the paper forward. So someone's going to pull on the paper as the pendulum is dripping sand out. Now, it's not going to trace a straight line anymore because now the paper is moving. It's going to create what's called a sine curve. It's going to look something like this. Now I'm going to take that sine curve that we just created there, and I'm going to turn it on its side to the left of this piece of paper, right here, or sorry, to the right. And I'm going to do it in blue. So a sine curve is a very special curve that describes this motion. This motion is called simple harmonic motion. Now there are a few pieces of the sine curve that you need to know. If we take a dotted line and we send it down the middle of the curve, we see that there are both crests and troughs. Now the distance from the top of one crest, I skipped forward a page, there we go. The distance from the top of one crest to the center line down the middle, right here, this portion is called the amplitude. And some of you might have noticed that this distance from the trough to the center line is also the same distance. So there are two ways to measure the amplitude. You can measure from the top of the crest to the midpoint, or from the bottom of the trough to the midpoint. Now, if we were to take, I'm going to skip forward. I'm going to grab this. Okay, I've extended our wave a little bit, so I have space here to do this whole thing. Okay, so now if you were to take a point on this graph, we can pick the bottom of the trough right here and go all the way over to the bottom of the next trough. This distance is called the wavelength. Now, this is the depiction of the time it took for the pendulum to swing all the way to one side and all the way back. If we go back to our drawing over here of our sand, you'll see that one wavelength was the pendulum swinging up the paper right here till it reached the top, and then back down all the way till it got to the same point on the bottom. That would be one cycle of the pendulum, is one wavelength. And we could start this wavelength anywhere. We could take it, instead of measuring from the bottom of the trough, we could measure from the top of the crest to the top of the next crest, or the middle of the wave. It wouldn't matter. The wavelength is the same regardless of where you start. It's just one complete cycle. And we call this the period. This word should be familiar to you guys because we talked about period early on in the year. The period is the time for one cycle. You can also think of it as the seconds per vibration. Now, there's one more term that you need to know from today that you're also familiar with. It's the frequency. So the frequency is the inverse of the period. It's number of cycles per time. So given this, we can say that the period is equal to 1 over the frequency or the frequency is equal to 1 over the period. So the period is going to tell you the time it takes to complete one cycle, and the frequency is going to tell you how many cycles are happening every second. So the longer the period, then the shorter the frequency. And the shorter the frequency, that's a bad way to think about it. You can think about it this way. If something has a long period, then it's not moving at a very fast frequency. It doesn't have a very high frequency. If something's moving back and forth really quickly, it means its period is really small, then its frequency is going to be very large. Okay, that is all you need to know from today's screencast. I will see you all tomorrow in class. Welcome back from spring break. It was nice to see your faces today in class.